Hi, my name is Daniel Hickok Xiang. I'm from St. Olaf College, and today I'm going to be talking about transfer matrices with an emphasis on how they can be used to look at the 1D Ising model. The transfer matrix method is a general technique for solving problems in physics and mathematics. This is typically used when a system may be broken up into a sequence of interacting subsystems, such as a mass spring chain, a beam of light reflecting off a layered material, or the interaction of spin states. The transfer matrix method can simplify the calculation of numerical solutions, but it can also produce analytical solutions in situations that are nearly impossible to describe otherwise. Because of its usefulness, the transfer matrix method has been applied to a broad variety of systems. You can find it in optics, material science, acoustics, and many other fields. In my last video, I looked at the transfer matrix approach to modeling a mass spring chain system. You can find a link to that video in the description. In that system, we used transfer matrices to encode information about the forces being exerted on adjacent springs as a function of their displacement. This model had two advantages. One is that we were able to more easily compute the displacements which corresponded to different modes of oscillations. This was especially useful when looking at non-uniform spring constants. The second advantage, which I didn't go through in my previous video, is that the transfer matrix method can be used to find analytical solutions when they exist. I won't go through that derivation here. You can find an excellent paper on it in the description, because what I'm really interested in today is how the transfer matrix method applies to the 1D Ising model. To give you some brief background, the Ising model is one approach to modeling the magnetic behavior of materials. We can approximate a given material as a lattice of spin states which interact with one another. There are many varieties of Ising models with different dimensions, interactions, and geometries. Today I will be looking at the one-dimensional Ising model with nearest neighbor interactions and an external magnetic field. The total energy of the system is determined by the orientation of the spin states. When a spin points in the same direction as the magnetic field, this is a lower energy state. If it points in the opposite direction, it's a higher state. Similarly, if adjacent spins point in the same direction, this is a lower energy state, while opposite directions corresponds to a higher state. This gives us the Hamiltonian shown here. To get information about a system, what we would really like to know is the partition function. Once the partition function is determined, we can solve for just about everything we would like to know about the system. The partition function can be written in terms of the Hamiltonian, as shown here, but we can solve this more easily if we define the partition function in terms of the trace of a matrix. This is where the transfer matrix method comes into play. Let's define the transfer matrix P such that P contains all the information about how adjacent spins can interact. If we associate the first row and column with positive spins, and the second row and column with negative spins, we can assign all four possible energy states. If there are n spins, then we need n transfer matrices, each operating on the next. The trace of this product is our partition function. Taking advantage of some matrix properties and the eigenvalues of our transfer matrix, we arrive at the general form of the partition function shown here. Armed with this, we can calculate anything we want about the system. There are many interesting properties to examine. However, I am most interested in the magnetization, given by this equation. I want to look at the magnetization because one of the most interesting properties of the 1D Ising model is that it does not undergo a phase transition as you change the temperature. Physically speaking, this means that without an external field, the magnetization is zero for all temperatures greater than zero. The strength of the particle interaction alone is not sufficient to cause the spins to align in the same direction at non-zero temperatures. If we plot our analytical solution using Mathematica, we can confirm this property, noting a constant magnetization of zero with no external field. Now let's look at what happens when we increase the field. With just a slight increase in the external magnetic field, the magnetization jumps to 100% around t equals 0. Even a small magnetic field lowers the parallel energy state enough to cause all the particles to align at low temperatures. Note the region of constant magnetization equal to 1. The length of this region is dependent on the strength of the interparticle interactions. This is measured by our constant J. As we increase J, note that the constant region increases, and decreases when we do the opposite. This makes sense since stronger interparticle interactions lowers the energy state of the parallel state. Now that we have a feel for the analytical solution, let's look at some simulation data. Here I've used the Metropolis algorithm to simulate a 1D Ising model at different temperatures. First, we get a second look at the case with zero external magnetic field. This looks pretty similar to our analytical solution, but the magnetization definitely becomes non-zero when t is greater than 0, indicating a phase transition. This discrepancy is disappointing, but not uncommon in Ising model simulations, as it results from the way the Metropolis algorithm decides which spins to flip. Our simulation for non-zero external fields looks pretty similar to our previous graph, restoring some confidence in the model. Lastly, let's take a look at what happens when we use a random distribution of h values centered around h equals 1. We can see that this looks similar to the h equals 1 case, but the magnetization does not increase quite as sharply. This makes sense since some spins have less incentive to align than in the constant h model. These kinds of random field models are useful because they can help account for fluctuations or impurities in a material. Overall, I hope I've been able to demonstrate some of the benefits of working with transfer matrices, in addition to giving a brief look at how they can be applied to the Ising model. Although the 1D model can seem pretty trivial, its relative simplicity makes it an attractive regime to examine before introducing more complexity such as higher dimensions. For more information about the transfer matrix method, mass spring chains, and the Ising model, please see these references. Thanks for watching.